So our next recorded talk is Dr. Porjesz. I don't know if I actually pronounced that correctly, but Anthony, take it away.
Good morning. I am going to give you a brief overview of the work we're doing in the Henry Begleiter Neurodynamics Lab, or HBNL, named for its founder, Dr. Henry Begleiter, who had his whole career at Downstate, and co-directed by Dr. Jacqueline Myers. The HBNL brings together considerable multidisciplinary expertise at the intersection of brain function, addiction, and genomics. And we do longitudinal studies who are able to look at brain and cognitive development and decline across the lifespan, and risk and resilience for substance use disorders, as well as psychosocial influences. The heart and soul of the HBNL is brain function. From the beginning, we have recorded EEG activity with non-invasive scalp electrodes to record the millisecond by millisecond activity in neural networks, which have excellent temporal resolution. We look at both resting state EEG in the various frequency bands with conventional measures, as well as newer measures such as functional connectivity in neural networks, among them EEG coherence and index of synchronization between brain regions. And we can look at interhemispheric and intrahemispheric coherence. Dr. Myers will be talking about that in a few moments. We also focus on the time-locked EEG oscillations during a task in tasks that are related to alcohol use disorder, or AUD, such as attentional memory, executive function, and reward networks, evaluation networks. So these brain function measures provide phenotypes for genetic and phenotypic analysis and longitudinal developmental studies. One of the first measures that we looked at was the well-known large P3 or P300 component that occurs between 300 and 700 milliseconds after the stimulus and is related to its significance, not its physical features. We reported that individuals with alcohol dependence had low P3 amplitudes. This did not recover with abstinence even as long as 10 years, and was thought to be due to the neurotoxic effects of alcohol on the brain, until we did a seminal study in our lab, which we published in Science in 1984, and were the first to report that high-risk sons of alcoholic fathers had low P3 amplitude prior to any exposure to alcohol. And this changed the thinking in the field, that rather than being due to the neurotoxic effects of alcohol in the brain, the low P3 precedes the development of alcoholism, or AUD. And since that time, low P3 in childhood has been found not to be specific to AUD, but a marker of risk for later addiction and neuropsychiatric disorders. We have also, in the meantime, with advanced time frequency methods, teased apart this P3, and one of the most important components is the frontal emanating theta oscillation, which we find is also low in AUD and in risk. And because of these findings of brain function markers preceding the exposure of high-risk individuals to AUD, and because around the same time studies were coming out of Scandinavia indicating that sons of alcoholic fathers were 4 times more likely to become alcoholic than the rest of the population, even if adopted away at birth, we formed the collaborative study on the genetics of alcoholism, known as COGA, to look at genetic influences. COGA today is a multidisciplinary collaboration of 11 sites throughout the United States, with expertise going from clinical care to molecular studies. We have 7 collection sites, including one at Howard University to increase our sample of African Americans. The COGA family design is a family study. We recruited alcohol-dependent probands from treatment facilities to be sure they were severely alcohol-dependent, and then we extended through those families to have large pedigrees, and we do extensive multimodal phenotyping on all family members from age 7 to 90. Clinical, neurophysiological, neurocognitive, behavioral, environmental, social, and of course DNA. So this gives us a large set of families ideal for genetic and phenotypic studies. Our large families, many of them are densely affected with AUD, so they're enriched. We have diverse families, many African American families, and genetically informative and good for studies, including large collaborations. In 2004, we launched the COGA prospective study, where we looked at the adolescent and young adult offspring from our families that were enrolled when they were between the ages of 12 to 22. And we have been retesting them with multimodal assessments every 2 years, and have a particular focus on frontal lobe function, which is very much in development and important during this time period. So some individuals have had as many as 8 tests, and this allows us to do developmental trajectories and gene bioenvironment interactions. Dr. Myers will be talking about her work using this sample. We also have been taking our original sample and following them as they enter later life, and we find they have a range of drinking patterns and symptoms 20 years later. An interesting finding is that EEG functional connectivity from 20 to 30 years ago predicts memory and blackout problems today. And I'm going to give you 2 examples of COGA's integrated approach. The first, we start with the frontal theta oscillations as a phenotype, and we did a GWAS study of that and found that we had a significant association in SNPs in the KCNJ6 gene, or GERK2, and we were able to look at the effect of those SNPs on our theta oscillation trajectories during adolescence and young adulthood in our prospective study, and found we had age and sex-specific effects in reward processing, and effects for AUD. In COGA, we also have a genomics pipeline. One aspect is that we're able to derive human iPSCs from our COGA sample, and we did so in individuals with high and low theta who are controls and alcohol dependent, and are doing studies in that regard. A second example of COGA's integrated approach moving beyond GWAS is we take large-scale GWAS from the field. We derive the PRS and apply that to various phenotypes, in this example here to EEG coherence, and here gene environment interaction with social environment in the prospective study, and Dr. Myers will be talking about her work in this momentarily. And again, with our genomics pipeline, we are doing functional studies in iPSCs and organoids in individuals with high and low PRS. And finally, to give you a snapshot of the COGA Brain Function Project, we have 3 related aims. One, to understand brain function in AMD. The second, to look at its developmental changes throughout the course of AUD. And the third, to look at genomic and polygenic influences on brain function in AUD. And Dr. Myers will be talking about this in a moment. Thank you.